Welcome. This is the fourth lecture of our theory of elasticities module number 11. In the last three lecture we have introduced photoelasticity and some basic concepts of optics. Essentially these optics theory boils down to our knowledge of simple harmonic motion. So, basically we learn two things mainly, that when you have a simple harmonic wave and if it is coming from two such direction in a perpendicular direction, then if you superpose those waves and then what will be the resultant wave, and then if these two waves are in a plane, then what if the superposition will lead to. So, these two theories or these two wave superposition we have learned. Another the reason we learned this, because the photoelastic experiment uses the instrument called polariscope, and polariscope is based on this principle, the superposition of wave. So, what happens is when you basically put a photoelastic material under testing in a polariscope, then it shows a characteristics of birefringence. The birefringence is that the material when not stressed or not loaded, essentially it shows the isotropic optical property, but when stressed it exhibits the anisotropic optical property. What does this anisotropic optical property means? The anisotropic optical property means that the refractive index in different direction of the material is different, but when you remove the load and when it become unstressed condition, then refractive index remains same in all three directions or three mutually perpendicular directions. So, this property is essentially known as the temporary doubly refractive refraction or temporary doubly refraction, and this kind of material is suitable for photoelastic experiment, and this phenomena is known as the birefringence. So, basically with this property the whole photoelastic experiments rely, or it uses this property, and this type of experimentation or this type of photoelastic experiment is also known as the transmission photoelasticity. So, we will discuss what is non-transmission photoelasticity in the last lecture in a brief outline we will give, and then once we are equipped with this basic optics, in this lecture essentially we will find out what is the theory of photoelasticity and what are the basic laws involved in it. So, the basic laws in photoelasticity is the stress optics law. So, before we get into stress optics law, so stress at a point essentially has 6 independent component, and then if these components coincides with the orthogonal or the principal direction, essentially then shear stress vanishes, and the stress at a point can be represented in terms of sigma 1, sigma 2 and sigma 3. So, sigma 1, sigma 2, sigma 3 are essentially the principal directions, and the stress at a point can be expressed in terms of 3 principal stresses. Now, these 3 principal stresses, the resultant stress also we can express, and this resultant stress is essentially your through the Cauchy's formula we can express. For instance, the resultant stress that is traction along x direction is sigma 1 nx, and sigma ty is sigma 1 sigma 2 in y, or we can just simply write in terms of this thing also. T1 is essentially sigma 1 in 1 and sigma T2 is sigma 2 in 2 and so on. So, this sigma 1, sigma 2 and sigma 3 and T1, T2, T3 represents a stress ellipsoid. So, if you manipulate this, or if you try to remove the this n1, n2, n3, that is your cos x or cos the direction cosines, essentially the angle between x and n axis, or one direction and the plane of normal, the normal direction. So, this n1, n2, n3 if you try to remove and then express this T1, T2, T3 in C1 sigma 1, sigma 2, sigma 3, then it represents an equation of ellipse, and this equation of ellipse is essentially T1 squared sigma 1 squared and plus T2 squared sigma 2 squared and T3 squared into sigma 3 squared equals to 1. So, this equation of ellipse is essentially this stress ellipsoid. So, for this each axis of this ellipsoid represents the value of principal stresses. So, this is another definition in terms of principal stresses at stress at a point. Now, this concept can be in case of a birefringent material, or the material which exhibits the anisotropic behavior of refractive index temporarily at least. So, this can be extended to index ellipsoid, or this formula is essentially valid for your index ellipsoid, or this formula can also be equivalent to the refractive index. So, if you have the refractive index of n1, n2 and n3 are 3 directions, then this can be represented in n1. This index ellipsoid is very similar to the stress ellipsoid. So, that naturally these two things are very much correlated. So, what I mean the correlation is that if you know the index ellipsoid, you can have the stress ellipsoid, or vice versa. So, that means the stress ellipsoid and index ellipsoid are related, and this is the basic principle of photoelasticity, or essentially the transmission photoelasticity. So, so the similarities between stress ellipsoid representation of a stress at a point and index ellipsoid representation of refractive indices at a point that presents that points out the presence of a relationship between stress and optical properties. So, it is naturally because in the last class also we have discussed this, that the material which exhibits or which shows the temporary double refractive properties or temporary double diffraction properties, then this kind of material is when it is loaded shows that anisotropic behavior of refractive indices. So, naturally when you load, that body is stressed. So, naturally this stress is connected with the refractive indices of the body. So, this finally leads to the stress optics law in photoelasticity, and this stress optics law is also known as the Maxwell's law. So, this stress optics law relates the change in refractive indices of a material exhibiting double diffraction or double refraction to a state of stress in material. So, essentially what it means that refractive indices are related with the stresses, and how it is related? The relation is that if you have n1, n2 and n3 are the 3 refractive indices, and the difference with the absolute n0, that is the refractive index of material in the unstressed stressed. So, relative change in the refractive indices when the body is stressed, it is equals to C1 sigma 1 and C2 into sigma 2 plus sigma 3. So, along the one direction. Similarly, for the other direction is C1 sigma 2 plus C2 sigma 3 plus sigma 1. Similarly, N3 minus N0 is C1 sigma 3 plus C2 sigma 1 plus sigma 2. So, this change or this relation is essentially known as the Maxwell's relation, and where the N1, N2, N3 are principal refractive indices in the stress state associated with principal stress direction. So, an N0 is the isotropic refractive indices of the material when the body is not at all stressed. Now, sigma 1, sigma 2 and sigma 3 are principal stresses in the material, and C1 and C2 are stress optics constant. So, this is a material constant essentially, this C1 and C2. So, this constant is a material property. So, stress optics constant. So, this three thing, if we know now the refractive indices and the stress optic constants, then we can find out the principal stresses with these three equations. So, this is the basic essence of the Maxwell's stress optics law. Now, if three principal axes and their corresponding refractive indices can be determined, the stress state state of stress at any point can be obtained. So, this is the basic formula or the basic laws of relation between stress and refractive indices. Now, with this law, we can essentially modify the stress optic law in terms of retardations. So, what does this retardation means is that when if I just now represent this stress optics law in terms of N1, N2 and N3, that is we try to remove N0, that is the previous unstressed refractive indices, then the stress optics law represents this, and this C is known as the relative stress optics coefficient, which is C2 minus C1, and this is expressed in terms of Brewster. The Brewster is the units of stress optic coefficient. So, essentially it is 1 by stress if you can see from this. So, it is meter square per Newton. So, this Brewster is essentially the unit of stress optics coefficient. So, finally, my stress optics law in terms of relative refractive indices is this. So, C into sigma 1 minus sigma 2, C into sigma 2 minus sigma 3 and C into sigma 3 minus sigma 1. So, this stress optics law is used essentially for finding out the stress difference or principal stress difference in case of a isochromatic fringes or isoclinic fringes. So, that we will see later. Now, once we know this, we can also find out in terms of retardation how the retardation means. So, as we know from the phase shift in a absolute air to the material, if the refractive index is n, then the linear phase shift delta I can expressed in terms of this. This is very simple formula, because if the light is propagating through the material, then delta is essentially h by, if h is the thickness of the material, h by v is the delta, and then h by v can be the delta is essentially h by v minus 1, that is h, because it is the relative distance. Now, similarly, if there are two material, the two axes, in two axes, delta 1 and delta 2 are phase shift, then the relative phase shift can also be expressed in terms of these two expression. Essentially delta is the relative phase shift, and the delta 1 minus delta 2 is h into n2 minus n. So, this N1 and N2 are the medium refractive indices or the directional refractive indices. If it is one, the N1 is representing the one direction one refractive indices, N2 represents the direction 2 refractive indices. So, linear phase shift, similar to the angular velocity, we can also define a term called angular phase shift. This angular phase shift is essentially 2 pi by lambda into the linear phase shift. So, this 2 pi by lambda and delta I can express in terms of 2 pi h lambda by N2 minus N1. Now, if you use this and with the previous stress optics law that we have discussed in the previous slide, so then delta 1 2 for N2 minus N1, we can write it in this form. So, this is essentially the stress optics law in terms of retardation. So, what does this delta 1 2 means? Let us see what does delta 1 2 mean. So, since a stress photoelastic material behaves like a wave plate. So, what does this mean? This means that it shows a different refractive indices, or essentially the propagation of light in different direction is different. The that means since the refractive indices becomes different in different direction, so the velocity of light essentially becomes different, and then the distance traveled by the light within the medium in different direction becomes different. So, the relative angular phase shift or relative retardation which is dependent on the refractive indices on that on the different axis can be related with the changes of the refractive indices. So, if a material with thickness h is oriented perpendicular to one of the principal stress direction at a point of interest and plane polarized light beam is passed through it normally, then the relative phase shift of the principal direction is this. So, what does this delta 1 2 means? Delta 1 2 is the magnitude of phase difference between two components of the wave propagating in sigma 1 and sigma 2 direction, whereas the incident light wave is propagating in the sigma 3 direction. So, essentially delta 1 2 means that it is the phase shift between the two orthogonal direction when the light is propagating along sigma 3 direction, or essentially the third direction light is propagating, and the two orthogonal direction, what is the relative phase shift. So, this is essence of the stress optics law. So, stress optics law here we have expressed in terms of retardation, that is the change or the how slow the light is along two orthogonal directions. But this is remember that if the refractive indices are not different along the 1 and 2 direction, the phase shift will not happen, because the stress optics law states that the refractive indices or the relative refractive indices is proportional to the relative change in the principal stresses. So, essentially delta 1 2 will be 0 if the material is unstressed, because the refractive indices will be isotropic in all direction. So, that means the birefringence property or the property of doubly refraction along different directions is essential for the photoelastic experiment. So, now in case of a 2D plane stress problem, we can just simply write it in this form, because in a sigma 1 and sigma 2, if we take sigma 3, then this phase shift can be written as 2 pi h c by lambda and sigma 1 minus sigma 2. Now, this 2 pi h c by lambda is where c is the your Brewster. So, Brewster is not commonly used. So, what we write is that lambda by c we define first, which is known as the material fringe value. So, this lambda by c is essentially material fringe value, which is a material constant essentially. So, material property of the photoelastic material. So, what it states that how the light will propagate through a photoelastic material. So, now if we write this, so this sigma 1 minus sigma 2, we write this n f a by h. Now, n is delta by 2 pi and f a is lambda by c, which is material fringe value. So, if you know material fringe value, if you know the angular phase shift, relative angular phase shift, or that means delta is the angular phase shift, delta by 2 pi if you know, and then if you know the thickness of the material. So, essentially you can calculate the relative change in the principal stresses, and with that you can really find out the principal stresses in different direction. So, essentially this is the stress optics law that we require. Now, this can also be extended for the if you want to have the purely elastic material, for instance, which is not true always, because we see the viscoelastic behavior of photoelastic material. So, even if we assume under low stress state or the relatively elastic regime, purely elastic regime, so plane stress state, we can find out the strains with these laws, because let us see how we can find out the strains. So, this is it. If a photoelastic material shows linear elastic behavior, then difference of principal strain can also be measured. So, we know from the basic elasticity relation what are the stress strain relations. So, these stress strain relations can be expressed in terms of this. So, this epsilon 1, epsilon 2 is the principal stress, principal strain, and which is related with the principal stress sigma 1 and sigma 2. So, this the difference in principal stress sigma epsilon 1 and epsilon 2 can be expressed in terms of principal stresses, difference in principal stresses. So, this if we plug into this stress optics law finally, then we can find out that difference in principal strain is in f epsilon by h. Now, n epsilon is essentially the material fringe constant with material parameter involved in it. So, that E by 1 minus nu is the plane stress for plane stress condition. This E by 1 minus nu into F A is essentially your material fringe constant for strain, principal strain difference. So, finally, we can find out the difference in principal strain from the stress optics law. So, what are the basic things that we learned here now? We learned here two important concepts. One is that the stress at a point can also be expressed in terms of principal stress, which is the very common argument, because if the directions the orientation of the axis in such that it is coincides with the principal stress direction, then the resultant stress or the stress vector essentially, or the traction vector, we can also express in terms of these principal stresses through the Cauchy's principle or the Cauchy's law. So, with this Cauchy's law, we can express the traction and the stress in terms of normals. So, now this expression can also be if we try to remove n1, n2, n3 or the direction cosines in different directions. So, we can get a relationship between the traction and the principal traction values and the principal stresses. So, this relation represents an equation of an ellipse, and this ellipse is known as the stress ellipsoid, which represents stress at a point. So, now similar to this phenomena, it has been observed that refractive indices also follows some ellipsoidal description. So, which is in case of a principal stress, it is N1, N2 and N3. So, it is known as the index ellipsoid. Now, this trace ellipsoid and index ellipsoids are correlated, and this is the basic principle of photoelasticity, because in a photoelastic material, when you stress it, it represents anisotropic behavior of the refractive indices. What it means? The means that refractive indices at different directions are different. Now, this property goes off when you unload the material or you remove the stress. So, it becomes a isotropic refractive indices. That means, at all direction the refractive indices are constant. Now, this property is also known as the birefringence. So, based on this birefringence property, we derive the stress optics law, or it is known as the Maxwell's law, which essentially states that the relative changes of the refractive indices is proportional with the relative changes in the principal stresses. Now, this stress optics law can also be expressed in terms of your retardation. That means, if light propagates in one direction, and then what are the retardation in two other orthogonal direction. So, that means we can compute the phase shift between the two orthogonal directions. So, we have derived the linear phase shift, we have derived the angular phase shift, and with this angular phase shift and linear phase shift, we finally write the stress optics law in a with the help of material fringe value, and the material fringe value is essentially C by lambda by C, and then this or C by lambda, whatever is that. So, this material fringe value can essentially represents the how light will propagate through a photoelastic material. So, that means the material which has to be the birefringent capability has to be there for photoelastic experiments. So, now this n is essentially the angular shift or relative angular shift, which is delta by 2 pi, and then h is the your thickness of the material. Now, with these values we can essentially calculate the difference between principal stresses, and if the material is purely elastic material, we can also find out the principal difference in principal strength. So, in that case the principal the material fringe constant will be modified in terms of material constant, which is if epsilon equals to E by 1 minus nu into Fa. So, I stop here today. So, in the next class actually we will try to learn what is isochromatic fringe and isoclinic fringe, and what is the effect on this stress optics law, and how essentially we can calculate the fringe isochromatic fringes. So, and what are the things that it will depend on. So, I stop here for today. Thank you.